Let me ask you this. We're going to do an example to shed clarity, to shed some light. Yay! Okay, so I want to do some what we might call forward problems. Do you know what we called forward problem in intermediate algebra and pre-calculus? We call it function evaluation. Because what's a function evaluation problem? What do I give you? The function and the input, and what do you give me back? The given output. That is literally what that is. It's just a very, very special function, right? Problem 1 is a function evaluation problem. You give me an input in a function, what do I tell you back if I solve problem 1? What the output is. Most teachers in linear algebra skip that problem. They don't even tell you that problem. You know where most people start linear algebra? This one. I find this to be just like asinine. Right? That's the equivalent of teaching you how to take integrals when you've never studied functions, you've never studied graph, you've never studied differentiation, and you walk, so the equivalent of the fundamental problems in linear algebra are studying of functions, basically. You're going to study like how to construct functions from the world around you, aka how do you construct vectors and matrices, right? Forward problem, you're going to study how to take derivatives in calculus. Then, after you know how to construct functions, know the graphs, understand where they show up, etc., and you know how to take derivatives, then what do we teach you in calculus? The backward problem. Why in the hell would we ever teach the backward problem before you've ever put your shoes on? It's like me teaching my son how to drive a car, he can't even walk. Right? That's a sin. So I refuse to do that, but as you talk with the other friends, first thing they're going to do is they're going to be dropped, they're going to be literally given an integer coefficient matrix, and then they're going to work on something called Gaussian elimination. That's going to be like week 7 for us. But by the time you get there, you're going to have one of the most sophisticated understandings of that content in lower division mathematics. I can promise you that. It's pretty cool. Okay, so forward problems are called function evaluation. You know what we call backward problems in our previous life? Algebra. Yeah, isn't every algebra problem, instead of me giving you the input to a function, I give you the output, and then you find the given x's that produce that output? That's an algebra problem, right? What would be a differential problem? If your equation was differential, not algebraic. We'll talk more about that later. Don't worry, don't worry. Okay, so this is called algebra, based on a very famous function. Okay, let's assume for a moment that we're not allowed linear functions. What's the next most interesting function that we might choose? Famous, yeah, we might call this quadratic function. In linear algebra, you might also call this what's known as a quadratic form. Mike and I are going to be playing with quadratic forms for the next 6 months in our life because energy calculations show up as quadratic forms. Okay, so what's the easiest quadratic function you could ever think of? Okay. So f of x is equal to x squared. Be careful, this is non-linear. Why is it non-linear? That's true. Yeah, it's not ax equal b. So this analogy that we're about to do only goes so far. And I'll show you exactly where it breaks down in just a second. All right. So let's think about the different types of backward problems we could solve. So my claim is, so let's do a forward problem. Let's do a forward problem. What's a forward problem here? What would you do? Yeah, so we would say let x be equal to, anybody have a favorite number? That's 2, that's a great number. Okay, what does that imply? F of x equals f of 2, so now I evaluate that function at 2. 2 squared is equal to positive 4. That was my unknown and desired output vector in the codomain. The moment I know that there exists a 2 in the domain, what do you immediately say about that thing? It's in the range. It must be in the range because the ordered pair, what's the ordered pair there in the course? 2, 4, right? That's in my function. So the way that I would write this in set theory, I would say 2, 4 is an element of my function. Okay, so that's the forward problem. let's think about the backward problem. And when I think about the backward problem, I actually want to consider 3 different possibilities. And those 3 possibilities are literally going to be the same type of possibilities that we talk about in the general linear systems problem. Okay, so let's talk. So this is what we call the backward problem. And we're going to say 3 options. Okay. Let's talk about option 1. All right. Could you just do me a real quick favor? Put your arm horizontal this way. And then let the center of your arm be the 0, 0 mark. And then with your right finger or left finger, depending on what you do, please draw the x squared function. You got it. You got it. Be careful. Real parabolas have curves. Fake parabolas are called absolute values, right? So you got to make it curved, right? Okay, so here we go. So here's this thing. Okay, let's look at the first one, which is called a unique solution. The first backward problem. What output value has guaranteed a unique solution? 0. So if I say let f of some unknown x, in this case we're going to call this function x squared be equal to 0, what does that immediately imply? Yeah, it implies that x squared, how do I undo a square? Square root. I take the square root of 0. What's the square root of 0? 0. Square root of x squared? Yeah, absolute value of x. There you go. So what's the one choice? 0. Yeah, so in this case we have x equals 0. That's a unique solution. Okay, so one choice for this backward problem is to have a unique solution. Okay, what's the second choice? Option 2. Non-unique solution. Okay, and what would that look like? Really? Say any other positive number. Any other positive. Yeah, there you go. Okay, so maybe I heard 1. I might actually use 4 for a second. The reason I want to use 4 is I want to show the difference between the forward problem and the backward problem, right? Okay, so what immediately when I say f of x equal to 4, what am I actually saying? X squared equal to 4. And then what do I do to undo that thing? Square root. What's the square root of x squared? Absolute value. That's a non-trivial statement. If I square root the left-hand side, what do you got to do to the right-hand side? It's the same thing. So this is now positive 2, absolute value of unknown x. And then what's the claim? Or negative 2. We're going to see this is where the analogy breaks down. There are multiple solutions in this case. How many solutions exactly? 2. In matrix vector multiplication, if a solution exists and it's not unique, we will have many, many, many more than just 2. So we'll talk more about that. But the analogy does apply. So the whole idea of this backward problem, what are the 2 different choices that we've had so far? Unique solution, non-unique solution. What's the third choice? Yeah. Option 3, let the output, and maybe, I don't know if you want to call this output b, be an element of the codomain of our function f, but b not an element of the range. Okay, so give me an example of that. So maybe we call that negative number negative 1, in which case we said we're looking for an x such that if we square that x, we get negative 1. What do we now say? Well, you got to be careful. No solution in R, right? Okay, and let's visualize that. Let's visualize that. So here's my function. Real parabolas have curves. Fake parabolas are called absolute values. Here's my negative 1. There's my point. What does it mean to have no solution? Yeah, no matter what x we put in, we'll never touch -1. Do you see something kind of special? Out of every single point, every single x, what do you know right there? But we can minimize the distance, and this is, we're not sure what this means, from outputs of f of x to our chosen value of b. What do I mean by that? What would the min be in this case? Yeah, if I chose any other x, this thing by Pythagoras basically, this would be guaranteed to be larger, right? This one right here, out of all possible x's that I could possibly choose, that input is going to be the minimum distance between the thing that I can't actually touch and the thing that is closest that I do touch, right?